Okay, this is a recap video for our lesson about projectile motion. What is projectile motion? Well, it's the flight of an object that's been thrown or shot into the air and then gravity is acting upon it. So if you throw a ball or shoot something from a cannon or from a gun or a firework or someone jumping off a diving board, all it needs to be is some object that is flying through the air that is not propelling itself. So only once you're in the air, it's only gravity. So once the ball's in the air, it's only gravity. Once a person's in the air, it's only gravity. It's not something, for example, like an airplane or a space shuttle, because those have engines and are going to move through the air differently. So, as we talked about before, projectile motion follows the shape of a parabola. This is the equation of a parabola or a quadratic relation in standard form. We have ax squared plus bx plus c, a little bit of a throwback to a couple of units ago. Two things we know right away. If the a value is negative, we're going to open down. So this parabola has a negative a value, it's going to open down. That makes sense, right, if we're talking about a ball flying through the air. The second thing that we know is the c value of a parabola in standard form is its y-intercept, or its initial value. So right away, before I've even looked at the question, if I have an equation in standard form, I know the initial value, which is the same as what we used to call, or we still do call, the y-intercept. And I also know the direction of opening. You know, if a is negative, it's going to open down. So right away, and I'd recommend this every time we do one of these questions, regardless of whether it asks for a sketch, I would always draw a sketch. So our initial value, our y-intercept, is at 0, 3. And then all we know is that it opens down. And having a sketch like this is going to help us interpret the rest of our analysis. So generally, height is going to be on our y-axis. This is how many meters above the ground the ball is. Let's say we're looking at a ball. So we've thrown the ball from 3 meters. Maybe I'm standing on the roof, or maybe I'm, on a platform and I'm throwing the ball. And then usually our horizontal, or our x-axis, might be time, how many seconds, or it might be distance, how many meters. But we're always going to see kind of height on one axis, and then time or distance on the other axis. So the first question we've actually already answered. What is the ball's initial height? Initial height is just another way to say what's the starting value. So we already know that the initial height is going to be 3 meters. Let's think for this question, h is meters. We're going to think about t in seconds. So the initial height is 3 meters. Initial height is just another way to say starting point or y-intercept. We could have also plugged in, well, the initial height is always when time is 0. I could have plugged in 0 for t. The next question says, how high is the ball after 2 seconds? Well, what does after 2 seconds really mean? After 2 seconds means that t is 2, right? So we've gone by 2 seconds, t is 2. So what I can do is I can still use this equation, but every time I see t, I'm going to plug in what we know it is, which is 2 seconds. So I can just copy that down. And if you have, we could do this, we could reduce this from however many steps we feel comfortable with. If you're using a scientific calculator, which hopefully you are for this course, I can plug that directly into my calculator and figure out the height in one step. So I'm going to type that in, negative 4.9 times 2 squared plus 20 times 2 plus 3. Okay, so after 2 seconds, the ball is 23.4 meters high. So if I know t, then I can plug it in and solve for h. So that would work to figure out the height of the ball after any amount of time. Next question is saying, when does the ball hit the ground? Well, what does hit the ground really mean? So I want to figure out, when does the ball have no height? So I'm trying to figure out really this point. We know at this point, we hit the ground, that's our x-intercept, or our zeros, or our root. So I have no height, and we're trying to figure out, well, how much time did that take? So whenever you see hit the ground, we want to be setting our height equal to 0. So the way these questions work is I have this equation that describes the path of the object through the air. And if I know one of the variables, either height or time, I can always solve for the other. So in this case, I know that height, I'm going to replace h with 0. And we're going to try to solve for t. And this will take a few more steps because this is now a quadratic equation. So I can solve that. Usually we solve that by factoring or using the quadratic formula. We've got decimals here. We're not going to be able to factor, so let's use the quadratic formula. The quadratic formula only works if I have an equation in standard form, which I do, and it's equal to 0. Okay, so we can go ahead. We know that A is negative 4.9, B is 20, and C is 3. And then if I want to solve for t, I'm going to use that quadratic formula, negative b plus or minus the square root of b squared minus 4ac, all over 2a. And then all I need to do is kind of plug in some of these values. Be really careful with negatives and positives. I like to plug in the numbers in brackets. So minus 4ac, remember that a is negative 4.9, c is 3, and it's all over 2 times a, which was negative 4.9. So we use the quadratic formula to solve for the time where it hits the ground. I'll just go through these steps a little bit quickly on this video. I know we've done similar videos before. I can do everything under the square root in one step, again using your calculator. If you want to use more steps, that's fine. So I've got this plus or minus the square root of 458.8 all over 2 times a, negative 9.8. So now I can split this up. So I have time is either equal to negative 20 plus the square root of 458.8 over negative 9.8, or the time could also equal negative 20 subtract. So that plus and minus in the quadratic formula means I've got to split into 2 equations. And again, I can just plug these into my calculator and solve. I like doing it in one step so I don't need to round too often or write down too many decimals. So I'm going to do my numerator, negative 20 plus the square root of 458.8. I'm going to evaluate that first and then divide by my denominator. So time could equal, and we'll see if this makes sense, negative 0.14. There's my T1. Or time could equal, and let's do the second equation. I realize that my calculator might not have been on the screen for that last one. I apologize. I've got to figure out this glare as well. So we've got negative 20, and this time I'm subtracting the square root of 458.8. and then dividing by my denominator. So time could also equals 4.2. Okay, we wanted to know when it hit the ground. Why do I have 2 different values for time? Well, if I look back on this parabola, every parabola is symmetric. So even though it doesn't really make sense in this question, there was another 0 or another root or another x-intercept with a negative, small negative value back to the left. So T1 makes sense mathematically. There is a second 0, but in this question we can say it's inadmissible. It doesn't make sense to have negative time in the context of the problem. The answer that we were really looking for was 4.2. That's our positive root. So sometimes, and the sketch really helps us determine this, one of our answers might make sense mathematically, but it doesn't make sense in our real life application. So the ball actually hits the ground, and we can kind of summarize this. The ball hits the ground after 4.2 seconds. So the idea of what we're doing in our projectile motion analysis is that if I have an equation that tracks the flight of the object, if I know one of the variables, I can solve for the other. So if I know time, I can just plug it in to solve for h. If I know h, I can plug it in to solve for t, and that will take a little bit of more work. We'll probably need to use the quadratic formula. Let's just do one more question with this same situation. Again, I think the sketch is going to help us analyze this. So this we can call part D. And I'm going to say for how long or for what duration, we'll say for how long is the ball above a height of 7 meters? So again, we're going to use this equation, and we're asking ourselves, well, do I know height or do I know time? Well, above a height of 7 meters, well, what that must mean is that we're going to have to set h equal to 7. So I'm going to set h equal to 7. And again, we're going to solve for t. So again, I have a quadratic equation, right? It's of degree 2. It's an equation. I'm going to solve for t. But I can't use the quadratic formula unless we have something in standard form. So I need 0 on one of the sides. So I'm going to move the positive 7 onto the other side. So I'm going to subtract 7 from both sides and then collect my terms. And now I have an equation in standard form. And when I solve this, I can use the quadratic formula again. A is 4.9, B is 20, C is now -4. I can solve this solution to figure out when the ball has a height of exactly 7 meters. So we'll do that. I'll try to do that a little bit quickly. If you want to fast forward through this part of the video, if you're comfortable with the mechanics of the quadratic formula, I've got -b plus or minus the square root of b squared minus 4 times a, careful your negatives, and c, all divided by 2 times a. So I really shouldn't have wrote an x there. We're used to x for a quadratic formula, but really here I'm solving for t. So what is t equal to? Well, it's -20 plus or minus. And again, we can put everything under the square root in our calculator in one step. If you have a scientific calculator or an Android phone, I know iPhones can be a little bit more finicky. You're welcome to take however many steps you'd like. So this time, the number under the square root, I'm actually square rooting in the same step now, is going to be plus or minus 17.9. So I did all of this in one step in my calculator and then divided by -9.8. Again, once I've simplified as much as I can, we're going to split into T1 and T2. There might be two possible answers whenever I use the quadratic formula. So first I have -20 plus 17.9 divided by -9.8. Then I also, and I might run out of space here, -20 minus 17.9 over -9.8. So again, I'm going to use my calculator to evaluate. Again, remember to evaluate your numerator first, and then I can divide by my denominator. So time always equals, or T1 equals 0.2 seconds. And then if I want to find T2, I'm going to now subtract 17.9 and then divide by, again, my denominator, which is still -9.8. I get time equals 3.9 seconds. Okay, I've got two answers. Well, what's going on here? And again, this is where a sketch can help us interpret our answers. Well, our ball is going to be at exactly 7 meters at 2 points. So it starts at 3 meters. Maybe it's not exactly to scale. Maybe here's the 7-meter point. So it does make sense that I've got two positive or two admissible answers. There's 1 point on the way up, right? This would be after 0.2 seconds, where it reaches a height of 7. And then it's also going to reach a height of 7 after 3.9 seconds. So when I solve for height, it does make sense that I could times have two answers. And what we wanted to figure out is how long is it above 7? So for all of this duration between these 2 points, the ball is above or higher than 7 meters. So to figure out how long it is, I can just subtract the smaller number from the larger. And so the ball is above 7 meters for 3.9 seconds. I've got a lot of writing on this page. But this is the type of projectile motion applications that we can do. We did a similar one in class. You've done a few of these for homework, or will do a few for homework. The idea is that I have an equation in standard form. I can, if I know t or h, if I know time or height, I can then solve for the other variable. And the quadratic formula is going to come into play a lot with these questions. So the challenge here, I think, is often figuring out what does the question want me to do? And then when I get an answer, how do I interpret it? And I think that's where drawing a sketch and slowing down is really going to help us. I know we're all pretty good at working through the mechanical steps of working with the quadratic formula. The trick is, how can I interpret and relate my answer back to the problem? That's all for this video. Again, if you have any questions or would like some extra practice with these concepts, please let me know by sending me an email. Okay, thanks for watching.